So we can use elementary matrices to discover a method for how to find the inverse of a matrix. And this will require some discussion of inverses and invertibility just in general. So suppose A is an invertible matrix. Okay, well, if A is invertible, then we've seen that AX equals B has a unique solution. And it's given in terms of the inverse, right? So the inverse allows us to determine that there's a unique solution. But if there's a unique solution, then we've seen from solving systems that that means that when we go to row reduce the augmented matrix, we end up with a situation where it looks like there's the identity matrix here, and then over here on the right hand side we have our solution. Okay, and so implicit in that statement then is that if A is invertible, A must be row reducible to the identity. And so if A is row reducible to the identity, then by what we just saw about elementary matrices, A must be equal to some product of the identity matrices. Or sorry, of the elementary matrices. I wrote that all wrong. Okay, so in case that last one is not clear, maybe let's back up just a second here. If A is row equivalent to the identity, then that means we could start with A, and then we could hit it by an elementary matrix, and then hit it by another elementary matrix, and so on and so forth. And after hitting it with enough elementary matrices, it would be equal to the identity, right? Okay, and we know that all of those elementary matrices are invertible. So I can multiply both sides on the left by EK inverse, and then the left side over here will become EK inverse. I mean times I, but who cares about the I, right? And then I can multiply on the left again by EK minus 1 inverse. And I have EK minus 1 inverse, and so on and so forth. And after doing this enough times, I will cancel off everything from this side, and I'll be left with A equals some product of elementary matrices. And so I guess I can put inverses on these ones right here. Doesn't really matter. The main point is that I just want to be able to say A is a product of elementary matrices. Okay, so now let's take a look at this situation. So this means that the same row operations that take A to the identity will take the identity to A inverse. Because if you back up to that that thing we had a moment ago, so a moment ago I said A is row equivalent to I, means that if we have A and then some elementary matrix and some other elementary matrix and so on and so forth, that I would get this equal to the identity. But what you may not have noticed is that this is actually a formula for the inverse. So this right here, since I'm multiplying it against A and getting to the identity, that is A inverse. Okay, so, and now if for no good reason whatsoever, I put an I here, because that definitely won't change the multiplication. I can always put in an I and nothing happens. Then look at what that's telling you. It's saying if you start with I and you do row operation 1 and then row operation 2 to the result and so on and so forth, and you keep on doing all these row operations, eventually it's going to take you to A inverse. So those same row operations, E1 corresponding to E1, E2, Ek, that back here took A to the identity, down here take the identity to A inverse. Okay, so then that's our strategy for how to find A inverse. What we're going to do is we're going to form the augmented matrix A adjoin the identity. So instead of augmenting with just a column, we're now augmenting with an entire identity matrix. And then we're going to do row operations until we get, well, something here. If we get the identity, then what we have over here is going to be, actually, why call it X? What we call, or what we end up with over here is going to be the identity. But that might not happen because not everything is invertible. So it might end up looking like the only other thing that can happen with a square matrix, if you don't get the identity, you get a row of zeros. And if you get a row of zeros, then this is just some garbage over here. So this is what you're going to have when A is invertible. And if in the case when A is not invertible, then you're going to end up with a row of zeros. And that also means that if you end up with a row of zeros, you know from that computation that A is not invertible. So in the next video, we'll do some examples of finding inverses using row operations like this.